Alright, there is a great number of these videos already out, but I'm going to kind of take this out with the anticipation of feeding it out to a couple of classes. Those of you that are going to be expected to have a deeper knowledge of doing some of this internal force calculation, and those of you who are just putting panels up on a roof, which is not a small thing. So I'm going to go ahead and draft the basics of drafting out a truss with a 40-foot span. I'm going to put the center line of my information on center line. I'm going to begin by drafting my first line without the box and all that from a point 0, 0, and I'll drive this flat in the XY plane, and later we'll tip it up 0, 0, 0, and then of course at 40 feet, working in a decimal at a 0-degree angle, zoom extents. Zoom out a little bit here. I am going to make it a 412 pitch. All kinds of different ways to do that, but I could do line from the end point at 12, 4, reverse, if you think about that. I can do left click, space bar, space bar, space bar, space bar. Ooh, I want to change my base point to the midpoint using the shift right click. And then also saying C for copy, going up here, and now I have my second side of that truss. I'm going to say F for fillet, hold the shift key, go from here to there. I now have my basic truss. I'm going to divide this one up into 3 pieces, which is, the command is divide, and I'm going to put that on, I guess I'll keep that on the same layer. We're going to use divide to divide this one up, and I'm going to just squiggle in the ones down here below. So this command of, remember, divide is really not a point command. You most use it with blocks, but here I'm going to use it with a point. One thing divide does is not actually divide up the thing. It just puts points in there, number of segments 3. I'm going to do the same thing here with 3. I'm going to now, if I could, erase that out and now do short pieces, line from the shift right click, the end point, shift right click the node, shift right click the node, shift right click the end point. I'm going to get rid of this one. Do line from the end here, shift right click the node, shift right click the node. Remember, point is the only thing with a node, and shift right click the node. So you can continue, node is not there, so that doesn't help me, but I can go shift right click the endpoint. You have to realize that even though very often this long truss is one piece, the theory is, in fact, that it's going to be treated as singular pieces when you do the computation of what's going on in a truss. So I'm going to now sketch the rest in and then do some breaks just to show you I'm really not concentrating now on doing the actual drafting per se, though I'm going to kind of visualize going halfway here. That would be 1, 2, 3, so 4. Let me try this. Divide. That into 4 pieces. I think I want 6. I'm sorry, we're going to make it into 6 pieces. This time take that out and realize that this piece here, I'm zooming in and out, that one there is going to come down here, and we're going to have all kinds of weird stuff. This is going to be a long piece in between here. So I'm going to do now this line from the end. For the first time, I'll show you shift right click, change the O snap settings to node. Change the O snap there, so now as I move close to something, it's going to grab what I want. Have a long run there, a run there. Whoa, and there my mouse is giving me screwy problems here. And then finally to the end point. Now, what I'm going to leave out is the naming of these nodes and everything else. I'm going to fill in the rest of the members. Line from the end point here to the node here to the node here to the node here. I'm going to go ahead and put this one to the endpoint and do the same thing on the other side, but once again you can learn, eventually you can left click, left click, left click, space bar. I'm sorry, left clicking on there, going space, 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 B for base point, which is actually right there, C for copy. Go ahead and set that up. And the mistake that's made here if you do something like this is in fact that you don't necessarily know where which direction these lines are going. So you would like these lines to be going up as you label these nodes. So we've got a truss here that looks pretty unstable to me. We'll talk about later how we go about. It looks unstable not only because it's unstable, because it's not, in fact, it's missing one thing, so I'll do that. You end up counting the number on a truss. One of the most important things you'll do is to count the number of nodes and the number of members. Shift right click to the endpoint again. And now we're to the point of determining interior stresses. We're going to visualize and play around with, how basic this is supposed to be. And we're going to show you now, we're going to make the assumption, now going to some weird layer that's green. We're going to make that our current layer, turn it on, click that. We're now going to draft a force up, and the force now you have to decide what is going to be your scale, so we'll make 1 unit equals 10 pounds. I'm going to just put a line from the endpoint here, and remember, this is now a reaction force. That's 5. We would have gone through that. We would have put that reaction force. There's that nasty little icon, UCS icon. You're going to turn that off, remembering that that is your 0, 0, though eventually you'll see you need to be able to shift 0, 0 around. If you want to use what I show you here as highlighted as I get to a point, the start and the delta for any particular line. And that's why, in fact, it's nice to know which direction your lines go. It's important sometimes that you have a line type that shows direction, but now let's assume that that is the only reaction force, and the reason that's there is because probably prior to that you had already done this calculation of something in the order of 100 going down being reacted to due to reactions, because you're figuring out what is your support, what is the stress underneath the bearing of your truss. Does it need to be put on a base plate? Does there need to be a steel plate there? Is it on masonry? Is it on brick? Is it on other wood? So this is essentially how it starts. You start with here. You use logic of putting reactions, putting your finger on a point that takes 2 of the unknowns out of the equation, and then solving by a sum of the moments. That all said, now let's show you the wipeout. Wipeout. And we're going to show you the wipeout command, W-I-P-E-O-U-T. Basically, we'll go a polyline, but it's going to kind of keep it kind of rough here. There, 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 and there's how you get the wipeout. Well, with that, you'll see some greater value because you can kind of get pretty close here. And now you can put a circle right there, and you're going to see essentially how, in effect, you can then also put a short line from near anywhere along this member, and that basically is going to be your internal reaction force. And now you're to this point. I'm going to now put a new layer. I guess I'll put a hidden layer, which shows you, in effect, what the moment arms are. And so mathematically, you'll see later what you'll sometimes want to do is change your 0, 0 to there, R cross F. In other words, this force has actually been predetermined. This is the reaction force inside. So I'm going to go ahead and now do a line from the center on top of the wipeout here, perpendicular to, you're drafting perpendicular to things, and the same thing here, line from the center of this perpendicular. And you can realize that if this is pushing up this way, this has to push back, and it's based on the ratio thereof. So now let's see if we can play around with some of the parametric stuff. So here's what we know. that the length of this, and this one we can now kind of, to make it easier for you to see, we can kind of move that as we want. Space bar, going to move that to the end point, because you remember you can slide those forces anywhere along a line of force. It is the interior force inside this member, however. We want it to be bigger than that because it is closer to that. And so we can hopefully change its length based on a calculation. With that, you go to parametric, which I don't see here. So I'm going to right click. And because I'm in an older version of AutoCAD, I do not have those tools. So you'll want to look at that, and I'm not going to do that then. So what I have is, I know that this is 5, and I can now list that. It is 13.33, and I can list that. It is 4.44, and I can get the 3.33. It's going to be more because it's closer, and I can take this one here. I'm going to go ahead now and even get rid of this. Going to copy this. Left click, space bar, C for copy to the end point. And now I'm going to left click, space bar, I'm going to rotate minus 90. Of course, I've grabbed them both, so that wasn't good. So I'm going to hit an undo here. I had both highlighted. I need to left click this one, left click space bar, minus 90. So now I know that this has to expand or scale up based on this ratio. And so I can basically go, if I want, use a reference this length, and a second length is going to be that, and it's going to scale this up. Let's see how that works. You have to visualize this and get that basically it's a torque problem. You need to start with a teeter-totter, start bending the teeter-totter out, and then you've got what's basically a lever. And so we need to visualize this and be able to do it graphically before you start throwing numbers in, because in reality programs are going to do it anyway. This is in effect the most single important thing to do so that you can continue to think creatively and then strategically about structures in terms of being not the sum of the forces so much, but the sum of the moments. And moment is a multiplying force. So let's see if we can do this now. We're going to left click, space bar, scale. Sure, we can scale that. Reference length. The reference length is going to be at from there to the end of this. The new reference length is going to be from the end point of here, and that didn't work. So I'm going to try it again this way. We'll try it again. I think we can do this. We can left click space bar, rotate, space bar, scale. Yep, we can do a scale, and we're going to reference. And my reference length is going to be from the end of that to the end of that. Trying to do the end here. Is it going to remember the end? Yep, the end. And our new length is going to be the end of that. Remember, it was more? So in that, you see, by playing around, using some tools, and we'll review what the tools covered here are, you get the concept of what's going on. The step we skipped, I'm going to point out now, I'll put that in yellow, is the fact that anytime you cut a structure, you have to replace the cut by the unknown. So I'm going to show the short little unknowns here. Once again, because I can use that shift right click near, right through a wipeout, and then shift right click near, right through the wipeout, and I can do the same thing there. Line, shift right click near, shift right click near, right through the wipeout. And once again, line, shift right click near, right through the wipeout, shift right click near. And if you think about it, the other thing that's incredibly important as you're putting the unknowns, and this may seem small, but it's not, is you want those unknowns always to be that kind of unit length. So we can then, if depending on how you want to do it, you can use that command to review lengthen, total length 1. I guess that was 1. Total length 1. Total length 1. And you have what in fact were the unknown forces. And so what we did here is we picked a point of rotation that was where these lines of force came together. You should be able to do that without a lot of drafting, because you're trying to learn how to visualize structures that are standing, not just plug numbers into the standard equation of R cross F, R cross F. And so, in other words, to solve this one down here, you pick that rotation point. You said it's more or less than the force that's applied. It's a reactive, internal reactive force. And then you had to think about it. Is it more or less? If it's shorter, therefore it's going to be more. And we did that scale thing. All right, so when you're done, what you could do realistically is put these on different layers. And then you can actually, probably a setting to change the wipeout. But in reality, what makes the wipeout pretty nice is to put it on a layer that doesn't plot, which we don't have, but I'll just put it on the viewport layer right now. And then what you do is you get this ability to white out when you're printing, and that's really not a great input. Right there, you see you get this general sense if that doesn't plot. You can kind of label things and yada, yada, yada. All right, so I'm going to finally point out here the ability to solve this one right here would have been done by doing a point of rotation about this point. And the ability to solve this one right there would have been to do a point of rotation about the original point here. That said, think about that. The way this is shown, this member here will have no force. And I want you to think about that now. If this has a value and this has a value, this can have no value. And later on, the final piece to see on this is, in fact, this member here cannot have any force on it under this load, because if you notice at this point here, there'd be nothing to wrong on that. So I take that back. So it may be a zero force member, but it's not necessarily one. And we'll talk about why because of this, basically, this configuration here. So you'll see in a truss, the steps are basically counting the number of joints and numbering the number of members. That will tell you something about whether it's statically determinate or not, or whether it is over, whether you've got redundancy in the truss. The second one is to identify zero force members. We'll talk about what that means, and other special members. The next one is to solve for the reactions. And the next one is to work through your truss through any set of means, but definitely learn how to visualize a truss in a 2D problem by cutting through 3 members, showing those, replacing those cuts with tension forces, and then looking for points of concurrency of 2 of the forces, and then using the lever method. So mathematically on this, you'll see this can also be very easily and will be done by using radial vectors and force stack vectors. Remember that torque is R cross F, and vectors make it all not only 2D but 3D. Things that we've used in this demonstration, which is a long one, were wipeout, and then the ability to snap through with nearest. We use scale based in a weird way based on reference. We use divide, and then we just kind of use the basics of showing things on a drawing that aren't just geometry but also forces. If you remember this here, if we assume that was 50, I'm going to list it again, that was 50, then in fact this one here is the internal force inside that member along the bottom is in fact 150. In other words, the ratio of this to this distance is 3 to 1. Thanks for listening.